So what a Sentinel value is the value that you use in a program that you let the user enter to indicate that it's the end of the data. So it has to be a value that's not completely valid, that's not valid at all. For example, if you're writing a program that's entering, scores, and there's no way they can score -1, then what you can do is you can say, please enter score or -1 to stop. And so they type -1 or whatever. Or please enter birth date or 000000 to stop, that kind of thing. Usually it's the score idea, please enter. But if -1 is a possible value, you have to come up with something else. And maybe you just make it where they type a word, quit, please enter score, or quit, or Q to stop, because Q is obviously not a valid score. Well, at least in the games I've ever played. So, Sentinel value equals a value that is not valid as data, and the program uses it to know when to stop processing. So example, please enter score or -1 to quit. That kind of thing. So pseudocode for a program like that might be something like this. Kind of like that. Now here indentation means a whole lot. This code has to be indented under while. This one has to be indented, unindented under while. Some languages have the curly braces to indicate where you start and stop indenting. One thing you can do to make it absolutely clear, and the book's not going to show this, but you can put end if there as a comment, and you can put end while there, and that shows you absolutely what's doing. So a while loop is something that repeats over and over. It checks the condition. It's kind of like an if statement. If score is not -1, right, this stuff will only happen if the score is not equal to -1. It'll stop. Or won't stop, it just won't go in there, right? So if the score is -1, it'll skip that statement. Same's true for while. It gets here, and while scores is not equal to -1, well, it's equal to 0, so it'll go in the first time, then it'll do this stuff. And then when it gets to the end of the loop, it comes back and it checks it again. Well, is the score equal to -1 now? Nope, go ahead and do this stuff. But if it does equal -1, then this is no longer true, so it falls through and it outputs the total. So that's a while loop. It repeats until the condition is no longer true. Now, when I actually program this, I do it in a different way that doesn't require you to have the condition repeated twice, right? We have the condition here and we have the condition here, and I don't really like that, but we can roll with this. There is something else wrong with this pseudocode. Well, when I say something else, for one thing, I made a typo there. Right. Can't check for something called scores. There wasn't anything called scores to begin with. There's only something called score. But also, we're adding something to the total. Well, what's the total? Conceptually, our brains understand it, but as we get more, into actually writing this in a Python, we would need to declare that total as well, because it has to be declared before you can use it. So, total is equal to 0. I stick that up there as well. Now, other than the fact that there's no stop down at the bottom, this is pretty good pseudocode at this point. If I wanted to make it even better, I would put an output statement or a print statement here telling the user what to enter, because otherwise they don't know that you're not supposed to enter a -1 until you're ready to quit. So one more thing I would go up here and do would be output a message, enter score or -1 to stop, like that. Okay, now that's perfect pseudocode. Well, maybe not perfect. That's kind of a bloated, egotistic statement, right? Looks good to me. Looks good to the prof. And it would be really, really easy to turn into Python. Now, I had a couple of texts over the weekend from people who wrote their pseudocode in idle and then tried to run it, and it doesn't run. That's absolutely true. If you write your pseudocode in Python, it's not going to run. Well, it's not going to run in any language because it's not a programming language. It's all loosey-goosey. It doesn't follow a specific grammar. It follows some kind of loose grammar rules. For example, the pseudocode in the book uses the word set. And I think I've already mentioned that some textbooks also don't like equal signs. They do, you know, some kind of fancy arrow like that. To me, that's useless fluff. If we see score equals 0, we know that it's setting the score equal to 0. And this is just really, really useless. I can't really see why to do that unless you're just really trying to draw the eye to that, right? Those arrows make your eyes zero in on that. And is that the most important part of the program? No, it's probably the least important. The most important part is how the loop works. So we're getting a little bit too far afield there. But I'll go ahead and obey the book, trying to obey the book. I'm going to leave it like that. And now I think that other than the fact that I've added some comments for the end if and the end while, I think that's pretty much what the book would write. So we could do a flowchart for that. Now, one thing the book shows is for beginning, these are called assignments. Assigning variables. And they put them in their own block in the pseudocode. Let's see if there was an example of that in Chapter 1, or if we have to hit Chapter 2 to see it. Now, in my mind, introducing the idea of Sentinel values this early in Chapter 1, before we even talked about how to do any programming and loops and stuff like that, was absurd. Oh, if we're only there, I may have leaped ahead. Okay. So, the idea behind a loop is so that you don't have to repeat the code over and over and over. Without a loop, the code might look like this. How many innings are there in baseball? 9, all right, unless it goes in overtime or whatever. So anyways, you could do this. This is stupid, but you could do this. Input score. Put a comment, score 1. Add score to total. Input score. Score 2. Add score to total. Input score. You see what I'm doing? I'm cutting and pasting the code and repeating it over and over and over. Anytime you're cutting and pasting code, that's an alarm bell saying that you ought to find another way to do this, that the code should be in its own module, its own function, or that it should be in a loop, or both of the above. Alright, now I get that to your brains, this may look better, right? Logic is cleaner, right? No loops, no if statements, it's clean, but trust me, writing something where you're cutting and pasting, where you're repeating the same action over and over is really not a good way to handle it. Why is that? For one thing, this only handles 9 innings. And as far as I understand baseball, which is not much, then if it's if the scores are equal, you don't call it a tie game, you keep going, right? Yeah, so how would we handle that logic for keeping going? We don't know how many, how long it's going to keep going or when it's going to keep going by this. Whereas with a loop, we could modify our loop, in order to handle it correctly. And plus, what if it was more complicated than just adding a score to total? What if it was calculating something with a complex complex equation, and it took several steps to, this code could become inordinately long and complex doing that. Or what if you didn't know how many numbers you were going to add together? What if you were taking all the rainfall readings for every county in the United States, which might be 2,500 or something if each state has 50 counties? I have no idea. You don't want to copy and paste this code 2,500 times. If any other programmer caught you doing that, they'd burst out laughing, and your boss would fire you. So you don't want to do that. You don't want to copy and paste code. Maybe if you only are repeating it twice in the program, that's okay. Any more than that, you absolutely should write it in a loop, put it in a function if it makes it more easy to understand later. So that's what loops are for, is so that if loops are for repeating, loops let your program repeat code until a certain condition, or until the condition is not met, is really how they're worded, but until a certain condition is no longer true. The example above is very bad code and should be coded as a loop. More like what the first code was. That's an example of it. Here all they're doing is multiplying numbers by 2 and printing out the number. And they wanted to do it 10,000 times. So would you repeat that code 10,000 times? No, that's bad. So here's our example of a flowchart with a loop, and it's an infinite loop, meaning that it would run forever until you killed the program. Back in the old days, that was a real problem. You might have to call the guys in the admin and have them kill the program. You might not be able to kill the program. Of course, nowadays you can just, click the window, or at absolute worst. I hope everybody who uses Windows knows how to do this. You've seen this, you right-click on something and do Start Task Manager. If you do that, then you can go and kill your program that way. That usually works. And if you're a Mac user, there's another utility that lets you do the same thing. Don't know why it's Find Activity Monitor or something like that. So this is a loop. It's not a good loop because there's no condition involved, meaning it repeats forever. You would want to put a condition. So making a decision, you test a value. Is the score not equal to -1? That's our condition. And as long as our score is not equal to -1, the loop is going to repeat. Flowcharts demonstrate decisions with diamonds. The diamonds are used for if statements, and they're also used for loops. So a Sentinel value is a dummy value that the user will never need, that is not valid data. And one example is end of file. Now the user doesn't enter that end of file, but if you open a file and you start reading into it, eventually you get into a state where there's no more data. And you can think of that as an end of file. It's the marker at the end of the file. Okay, so these are loops. Start. Input my number. Is my number equal to 0? Or -1 in this case. If my number is equal to 0, then stop. No, multiply it by 2, output it, and repeat. And it says don't do it. It's not structured. You'll learn about structure in Chapter 3. Honestly, I think this is a great way to handle it. I disagree with the book, but you'll hear me say that sometimes. You can never go wrong with just giving me an answer that's based on the book, but I'd also like for you to, listen to what I say and understand when I say why. Not that I've said why yet. All right, that's just the same slide. Now, let me guess. They don't show you the correct way to do it. They say it's wrong. They don't. Okay, yeah, that's great. So, understanding programming environments. When you're writing program, you enter text. You do that through a text editor. IDLE happens to come with a text editor. What we tend to use are integrated development environments, IDE, where they have a text editor built in with some other tools, and the other tools involve compiling the program, being able to run it, being able to test it, see the output right there. And in old school programming, you didn't have integrated development environments. You just wrote a text file, and then you ran a program on it that would turn it into an executable. And then maybe you had to run a linker, which would turn that executable into another kind of executable, and then you could run it. And you were typing all this stuff in just on a command line to get it to work. But this is no longer the 70s. We have IDEs. So it provides an editor, compiler, and other programming tools. One of the most famous, most full-featured is the Microsoft Visual Studio for writing Windows programs. It's an extraordinarily powerful IDE. Now, obviously, Linux users are not going to be using it. Mac users are not going to be using it, and those things come with their own IDEs. IDLE is also an IDE. I guess IDLE. Understanding user environments, the command line. You've seen me pop open the command line, and every time you run your Python program, it opens up kind of a pretend command line called the shell. We've seen that, where you can type entries into it. Or you can have graphical user interfaces, or GUIs, which allows users to interact with the program in a graphical environment. So that was a good thing, a giant leap for man and womankind. Why is that? Because our brains think more graphically, at least a lot of people's brains think more graphically than they do in terms of text, right? If you have to pick a file to open, a lot of people would rather go and double click on that file, look at a window, move that window around, rather than type in dir and then type in open space file name. Now, I've noticed that if you have a list like this, yeah, the icons are kind of useful, but it's the name of the ones that actually make sense to me. And I don't know if any of y'all ever used the versions of Word that didn't have what's called the ribbon. I don't remember when they introduced the so-called ribbon in the 90s or what. You see this? Instead of drop-down menus with text, y'all have seen those in other programs. You click File, and that lists a whole bunch of commands. It's text. Nope, not Microsoft. They make it so that if you click on, Home or whatever, you don't get a list. Instead, you have to look through all these buttons for the feature that you're looking for. So, is that an advantage? Well, maybe once you learn where all that stuff is, maybe it's an advantage. If you want to center your text, you don't have to go do Edit, Format, Center, or whatever. You can just zero in on it. Different people's brains work different ways. The Mac version supports both of them. Has both a menu bar up at the top with drop-down menus, and it's got the ribbon, just to get people, to cater to both audiences. So this is an IDE. Everything you use in Windows is an IDE, right? Not an IDE, I'm sorry, a GUI, a graphical user interface. You almost never, as a Windows user, pop open a command line and go and edit and run things there. And when I say almost never, I'm not sure if anybody has a need to do that anymore unless they're a system administrator or something like that, or they're using something Linuxy or Unixy where where that's more common. All right, we're about at the end of that. I'm skipping some of this stuff because I do expect y'all to read the text, so I'm not going to lecture 5 minutes on every slide. Understanding the evolution of programming models. People have been writing modern computer programs since the 40s. Newer programming languages. They're designed to look more like natural language, right? You don't want to write in ones and zeros like the poor folks did, in the 1940s. I'm going to show y'all something. I don't think I did this when I was babbling about the history of computers. Oh, that's not what I wanted. I guess that's a character named Altair. Alrighty. This was one of the very, very, very first home computers, before the Apple, before the Ataris and Commodores and Radio Shack computers and stuff like that. You'd order a kit from the back of Popular Mechanics or whatever, and you get this thing home and you build it, and then you'd look at it wondering what you were supposed to do with it. Notice a few things about this computer. Does it have a keyboard? Nope. Does it have a monitor? Nope. Does it have something in the back that'll hook it up to a TV? Nope. This is all you got. So how did you program it? You flip switches, and then you hit a switch that was kind of like the enter key on your keyboard. Then you flip the switches again, setting, switches has two positions, 0 and 1, and then you do it again. So you were typing in commands, byte by byte, like that. And then you'd finally hit a switch that said run. And what would it do? It would flash the lights in some way. Okay, that's gripping, huh? But the 1975, if you were the kind of person who was into, projects like that, you probably thought that was a big deal. And then another thing you could order from the back of Popular Mechanics was what was called a TV typewriter. And all it was is a keyboard that you hooked up to your TV like an old Atari. Except when you type stuff, it put the letters on the screen. Could you do anything with the letters on the screen once you got them on the screen? Could you print them out? Could you edit them? Really? Not really, but people combined that with this, the kind of people who are interested in building this in the first place probably had the ability to do that. And so then you did have your typewriter, and then you could wire this up to display on the screen, and you get your incredibly primitive, home computer. So this was part of what was known as the homebrew computer scene. It was kind of centered around, Silicon Valley. And engineers, at the companies there, like Hewlett-Packard and stuff like that, were all kind of competing to build the best home computer. And that was the birthplace of the Apple, computers. The Apple I was just a kit that you bought, came in a bag, or maybe if you were really lucky, it came, with a wooden computer case, or probably you build that yourself. So it was a revolution when people started making home computers and selling them from companies, Radio Shack and Apple, and very quickly followed by other ones, so that you could actually do your computing at home. So you wouldn't want to write your programs flipping switches, or at least I wouldn't. Instead, you'd rather write them in terms of English type languages, and I think I showed y'all examples of assembler code where, instead of typing in numbers, you had the ability to give, each command as like a 3-letter acronym or whatever. Move, jump, copy, stuff like that. And it still looked like an alien language, that you might find written on the side of a spaceship. But, it was certainly a lot easier to understand than just zeros and ones. And so that was great, but people very, very quickly wanted the ability to write the programs without having to do that kind of stuff. So compilers were invented in the 50s, and I think the big 3 languages were Fortran, COBOL, and Lisp. Now Lisp was a very computer science-y type language, not used for businesses and stuff like that. And so it got used at places like MIT and Cornell, where they had computer classes and stuff like that. But Fortran and COBOL are actually used today. Now they don't look the same anymore. The languages have evolved quite a bit. But they still are. They each have their own purposes. Mostly the COBOL programmers are just updating the software that was written 20 or 30 years ago. And so that's going to all get phased out eventually. In Fortran, though, people are still writing new software in it. I don't know the reasons why. So those are the ones where you have the English-like syntax and you have the algebraic expression, which we've seen like in Python, where you have if statements, the word if, and you have, A is equal to B times C, algebra. You have the word print and stuff like that. So it looks like English or whatever. And if you weren't English, if you were Spanish or whatever, you could write, your own functions. I don't know what the Spanish term for print or input are, but write your own functions with the names that you liked in your own language. So newer programming languages look much more like natural language, natural meaning, languages that we speak. So they're easy to use. You can create self-contained modules. You can piece those modules in a variety of ways. You can be absolutely sure that these Windows programs that Microsoft gives you share a lot of code just for displaying the menu bars up at the top and the scroll bars, down the side and stuff like that. Because if you can borrow code from another program you've written, you're going to be able to be 10 or 100 times fast than if you just have to rewrite the whole thing every time. Python comes with math functions like square root and sine and cosine and all those things you could write your own algorithms for. But you don't want to sit there and write an algorithm to how to calculate a square root. If you could just do math.square root, right? One line of code. Instead of writing, opening a math textbook tells you an algorithm for, doing square roots. So procedural programming is the idea that you have the program follows a series of tasks. And that's a lot of what we're going to be doing in this class. I hope that we get to some graphical user interfaces. I'm going to have to make sure that we have time for that. But, input data, process the data, call a function. It's all very linear, top to bottom kind of stuff. So then there's object-oriented programming, which focuses on things. I have a window. You might click this button. You have a printer. The printer has a printer queue. Everything is defined in an object. The window is an object. The button is an object. The printer is an object. The printer contains a queue, which is an object. And then so you list everything that the object can do. Well, the printer can do a lot of things. It can accept a job. It can cancel a job. It can return a queue list, right? That kind of stuff. So our summary. Hardware and software accomplish input, processing, and output. The logic must be developed correctly. If you have bad logic, you're going to get the wrong answers. For example, last week, Elon Musk sent up the spaceship with one of his Tesla cars, and that was a big deal. Lots of people watched it, over live streaming or whatever. I read somewhere that, that was the millennials equivalent to the moon landing. It's the only time that people are ever going to get excited about, rockets ever again. I don't know if that's accurate or whatever. But, people are, NASA and the other countries' space administrations are always sending space probes to other planets to learn about them, or comets or whatever. And a lot of the Russian space probes to Mars failed, whereas Russia is a powerhouse, in building rockets or whatever. Something kept going wrong for a lot of them. And, then America had to prove that they could get them just as wrong when they sent up an extraordinarily expensive, lander to go to Mars. And what it did is it, went into Mars orbit, and then it fired its rocket engines and slammed right into it. And it did, it wasn't a malfunction of the hardware. It did exactly what it was programmed to do. Unfortunately, it had been programmed so that the engines and things like that were expecting metric units, but that the instruments and the data in it were English units, right? Feet, yards, miles, and stuff like that, as opposed to centimeters. So that was a huge logic error. And the programmers who arranged for that, probably got fired. Whoops, you blew away your $1.5 million lander, because you gave it data, in English units rather than metric or whatever. So logic errors are really serious, bad things. Another one were the Patriot anti-missile systems. One of the bugs in that was that the longer you left it on, it introduced a timing error so that it took longer and longer for it, to respond to things. And when a missile's coming towards you and you're trying to shoot it down, you don't need it delaying a second before it, pivots the, the missiles and programs of guidance, to try to shoot it down. And so what the soldiers wound up having to do is to unplug and replug, or they, effectively reboot it every day to make sure that that timing loop was wrong. And they only started doing that after, considerable experience in the field because it wasn't found in testing. That's another logic error, having a timing loop that, that continued to add error into your program until it was no longer working. So logic must be developed correctly. Logical errors are much more difficult to locate than syntax errors, right? That logic error was detected after the thing slammed into Mars, or until the Patriot missile system started missing missiles that it should have been able to shoot down. You use your flowcharts and your pseudocode to plan the logic. You avoid infinite loops by testing for a Sentinel value. There are other kinds of loops, not just Sentinel value-based ones. Like a loop might be wait until the user clicks the close box in the corner of the window. That's not a Sentinel loop, but they did something that told it to stop. Or you might write a program that just executes a certain number of times. You're going to calculate pi via an algorithm, and that algorithm might run 10 times, in which case it'll give you a really lousy version of pi. It might run 100 times, which will give you a better version of pi. It might run 10,000 times, which will give you a more accurate version of pi still. And there's always kind of a contest among a certain style of computer, scientists and students writing their doctoral theses for how accurate you can calculate pi. And if you can calculate pi out to 100,000 digits, that's really awesome. And then if you can calculate it out to 600,000, you can be sure that it's looping a certain number of times to get that accuracy. And so, you tell the program that you're going to execute 10 billion times, whatever. There's got to be some counter that's keeping it to repeat, from time 1 out to time 10 billion, and you hope that, nobody shuts the computer off in the meantime, something like that. You use a text editor or an IDE to enter your program statements. Then you run the program. You test your program. All right. I should do a flowchart for that score program, but I'd rather actually write it in idle, maybe then do a flowchart. In my brain, people understand the flowcharts more if they've actually seen it in action. So let's go ahead and write a program that will kind of match that pseudocode that we did here. That one right there. But we're going to write it in Python and actually make it work. Now the book assumes that you might be doing this in Java or C++ or stuff like that, and it's not until this version of the text that they added any Python stuff at all. But the logic in those languages is the same. So after we get used to writing Python, you ought to be able to read the code that was written in Java or C++ and go, yeah, I understand what it's doing. I don't really know that syntax, but I know what it's doing. I understand what a while or an if is. Let's pop open idle. Now remember, never enter your code into the shell. You see those 3 arrows, it means move along, go and actually do a file, new file. So I'm going to put my name and the program assignment or whatever, the date. And this is going to be called Sentinel Value Demonstration with loop. Something like that. And you can break this all out into 3 comments. You don't have to put it all on one comment. Called a comment block. Never a bad idea to stick a comment block up at the top. And I would really like all of y'all to, at the very least, put your name and the date or something like that. The assignment number if it comes from an assignment. Just to show that you have the idea of writing professional code, which is commented. Alrighty, so if we were looking at our code here, our pseudocode here, remember that that's not a Python word. You just ignore that. When I started teaching pseudocode in the past, I tended to want to leave that word off, but I went ahead and did it because that's just proper. And why do I say that? Because in Python, everything needs to be indented properly, and just starting your code off with an indentation like that would be a syntax error. So I am going to put the word start there as a comment, just so that there's a correspondence there. But I'm not going to start indenting there yet. Now if I have a set statement, it's pretty much just the same thing without the set. Instead of writing this in this loose of English, I'm going to use a symbol that means not equal. If you want to, don't type this because I'm going to erase it, but if you, I guess I could add it to the notes. That means equals to. So like if you write if A equal 10, that means if A equals 10. But then there's another one, exclamation equal, which means not equal to. So if A equals 10. That's the Python code. The rest of these are just comments. This means not equal. Or is not equal to. You exclamation mark, just pronounce it as not. Sometimes when I'm reading code aloud as I type it, I won't remember to say exclamation point. I may say not. So this means if A not equal to 10. Now spacing is usually unimportant in these languages, where I could get away with doing that, but you can't put a space between that and that. So this means if A not equal to 10. Okay, I'm going to cut that stuff and I'm actually going to paste it into the text file because it's not part of our program. So as you always, I highlight everything just by hitting Shift down arrow, and then I hit Control X to copy it and Control V to paste it because I like keyboard shortcuts. Alright, where were we before I digressed? Here we go. While score is not -1. So while score not equal -1. And in this language, every time you start indenting, you need a colon on the line above. And when I'm wandering around helping people, half the errors in the first few weeks of the class are always because people forgot the colon. And that is a colon, not a semicolon. So instead of output, it's a print statement. Print, enter score, or -1 to stop. I'm going to drag this over so the window's a little bit bigger. Now I think I've mentioned that whenever we see the line input in pseudocode, we have to make it 2 lines in Python, which is an input and then a conversion to a number. So score is equal to input, and then score is equal to float score. So we get the data. So that's the input step and that's the convert step. Now once you get used to that concept, you may be tempted to put the convert step there under the input step in your pseudocode or flowchart. If you feel like it, that's fine. But really, that's almost useless frippery. It's polishing it. Why do I say that? Because in a lot of languages you don't need to convert it after you input it. So why put something here why put something in the pseudocode or the flowchart that not everyone would need? On the other hand, if I was writing some pseudocode that I wanted to give to a Python programmer and make it absolutely simple for them to do it, I might actually put the convert step in the pseudocode. Alrighty, so we've done this, input the score. Now we need to check the if statement. If score not equal to -1, meaning it's valid data, why wouldn't I say if score equals -1? Because we're not supposed to do anything if it equals -1. We're not supposed to add it to the total. So we have to reverse the logic. If the score is not equal to -1, add it to the total. Total equals total plus score. And again, since I indented an extra level, I need a colon on the line above. Now for those of y'all who type along rather than look at the screen, you type along based on what I say. I apologize for not always saying colon when I'm writing an if statement. I really try hard to do that. Alright, and then so I am going to put that comment in diff. Do you have to do that? No, but I think it helps. And I am going to put this in while comment because I think that it also makes it easier to understand. Helps keep track of your indentation levels. Every time you sit and type in an end, you know that the next line is going to be dedented one to the left. Alrighty, so now we need to output the total. Print, the total is, end quote, comma, total, like that. Now we're down at the end. We have a stop here. We can just put that in as a comment if we feel like it. Again, all of these comments are not necessary. I'm putting them there just to try to make the program easier to follow. But when I write all of my code, once we skip the pseudocode step, I may not always put a # end if, and I may not always put a # end while. All right, I wonder if that works. I'm going to save it. Don't save it in a Python 3632 directory. Put it in your work directory. It's not January anymore. February 13.py. In some languages, you can't put spaces in the file names. But since you can in this one, I'm taking advantage of it. All right, so I saved it by hitting Control-S. The only advantage to doing that is when I run the module, I don't have to say yes. I would like to save it. Okay, enter score, -1 to stop. I made 100. I made a 90. I made an 80. Uh-oh. Then I made 100. I'm tired of entering scores, -1. So that's the total. We could also calculate the average, right? The average is the total divided by the number of scores. For us to do that, we would also have to keep track of the number of scores. So I made the simplest example possible. Shouldn't quite say that. There are simpler ways of implementing this. And by I shouldn't say simpler, but ones that take up fewer lines of code. I'm going to remove these comments for a while and just let you look at it and see if you like the way it looks better. And then I'm going to do walkabout and make sure that everybody got it running. See, if we took those out and we took those out, some people think that looks cleaner, right? Less visual noise. It's always a balance. If the comments are just adding visual noise to it and they're making it more difficult for you to understand and follow the code, you can remove them. A professional Python programmer would think that you're very strange for putting end ifs and end whiles. They would think that it was adding visual noise. But we're beginning, so, you know, like training wheels. You put training wheels on the 5-year-old kid's bike, and then you take them off after you find out, you know, that they're not really helping them very much. So I am going to undo that and put those comments back there. All right. Walk around, see who needs some typo correction. All right, so we've written a program. We took some notes. We definitely need to remember to make a flowchart, a Dropbox for it. I think I'll take the time to do that. So that was in Class C. Alrighty, I'm going to go grab Chapter 2's PowerPoint. Any questions over what we've done so far? Maybe we won't do Chapter 2. Wow. Alrighty, I was able to preview it and you were not. Of course, y'all can read it in MindTap, but I'm also very fond of just downloading the PowerPoint. If it doesn't work for you, I apologize. if you really want a copy of it and you can't download it, I could always mail it to you. Maybe I'll zip them all up and just put them on an attachment as the notice so that you can get them that way. All right, elements of high quality programs. In fact, why don't I do that now? Second thought, I'm going to do it later because I'm not seeing that pop up either. Oh, it's down here, isn't it? All right, if you want it, download it on your machine. Go back to the front page by clicking on the CIT1113, and there's a zip file you can download and get it. Elements of high quality programs. So we're going to learn about declaring and using variables and constants, performing arithmetic operations, the advantages of modularization, modularizing a program, hierarchy charts, and features of good programming design. Some of the stuff we already know. We know how to declare and use a variable. Total is equal to 0. Total equals total plus score. That kind of thing. We've done a little bit of arithmetic. Not a whole lot. Mostly we've just added things to totals. Maybe we did a payroll at the beginning. I don't recall. So data types. A data type describes what value can be held by the item, how the item is stored in memory, and what operations can be performed on the item. So for example, in some languages, you can't use a power of, an exponent feature on a floating point number, which is weird, but you can't say 2 to the power of 3.4. Or you can't do modulus on a floating point number. So some things you could only do on integers, some things you can do on floating point numbers. There's another data type called string, and you can't do math on a string at all, which is why we always have that conversion step. Float is, x is equal to float x. So the three things that a variable consists of. They have a type, data type, they have a name, and they have a value. So if you do x is equal to 0, the name of it is x. The type is, if we eyeball it, that's a whole number, so we know the type is an int. And the value is 0. If I give you a statement like that, you ought to be able to tell me the name, the type, and the value. And how do you tell what the type is? Well, you can always type it. You can always tell by what's being assigned to it. Now, that's a little more complicated. If it was like x is equal to y, you'd have to figure out what y was. Now, idle gives us a little bit of help there, because you could always go to the Python shell and just say type. Okay, I didn't remember what a 0 is. Oh, a 0 is an int. Or how about type of somebody's name? It says, oh, that's a string. So until you have them all memorized, which I would expect you to be able to do so pretty quickly because we only have 3. What is the type of something with a decimal point? Float. Okay, so we have 3 types. So x is equal to 0.0. It's got a decimal point, so its name is x. Its type is float, because it's got a decimal point. And its value is 0.0. Lastly, x is equal to quote 0. And if you like, you can use apostrophes. In this language, unlike some, you can use them interchangeably as long as they both match. You start with an apostrophe, you better end with an apostrophe. So the type is a string, because anything surrounded by quotes is a string, and then the value is 0. This looks like a number, right? But it's not a number. It has to be converted to a number before we can use it. That's why we do score is equal to float score. Had to convert it to a number before we could start adding it on to things. Because the computer doesn't know what's in there. We could have typed in Jeff. You know, enter your score, -1 to continue. Type in Jeff, it's going to crash because you can't do math with the word Jeff. Or if you accidentally hit space and enter, well, that space is not a number. It can't add space to the total. So the type determines what kind of data it is and what operations, like addition, multiplication, or whatever, or functions, can be used with it. Now in this language, ints and floats are pretty much interchangeable. They're stored differently inside the computer, but you can add 2 ints, you can add 2 floats, you can add an int to a float, you can divide an int by a float. So they're pretty much interchangeable. The only difference, the big difference, is that ints are whole numbers and they never get rounding errors, whereas floating point numbers do get rounding errors, and we'll talk about that. Constants. Now this language isn't big on constants the way some of the others are. So there's no way to tell the language that a number is a constant. Well, what's a constant? If you were going to write a program that looked like this, area of a circle is equal to pi r squared, pi times r to the power of 2. It'd be neat to say that pi is equal to 3.14159, and then if you wanted to, you could, take it out to 10 digits or 20 digits or whatever. This is done in capital letters to indicate that it's a constant. An experienced programmer will think to themselves, okay, if that thing is in capital letters, it means I shouldn't change the value, right? Because if you turn around later and decide that pi is equal to 3 or pi is equal to cherry, something like that, the rest of the program, if you ever repeat that, is not going to work because pi is obviously not equal to 3, and you certainly couldn't do math with the word cherry. So if you see a variable in caps, it means that the programmer intended for it to be a constant. Now in some languages, you can use the word const in front of the variable, not Python, so don't memorize that, to flat out say that number can't be changed. And then if Mr. Clueless programmer who comes in and tries to change it, that would crash the program, or it won't even compile, one of the two, because you can't change it. You're saying, you're kind of creating a contract with the program saying this value cannot change. What if you had a typo in it? Well, then you, the programmer, have to go and modify the code to fix the typo. What if you have sales tax is equal to 8.5? And then the city changes the sales tax. Well, you have to go and you have to change the sales tax. But you would not want to have used that 8.5 100 times in your programs. If instead you made it a constant, I'm going to remove that word constant. So if you had that in there and you use sales tax everywhere you were going to calculate it, like total is equal to price times sales tax times the price, something like that. I have the equation wrong. There we go, like that. And then you use that variable 10 or 20 times in it, you'd only have to change it in one place. You go to the top of the program and change that 8.5 to 9 because they bumped the sales tax. So a constant is a value that shouldn't be changed, or in some programming languages can't be changed except by the editor changing the source code. Now, I'll give you an aside on that. If you were going to have the sales tax in there, you probably would not want to just store it in a constant. You would want to be able to store it externally so that it could be changed for all your programs or something like that. I don't know. But anyways, that's the idea of a constant. Some number that you're going to use that's not input by the user. The user doesn't type in pi. You know, if you're going to calculate the area of a circle, you do not say, please tell me the radius of the circle, and they enter 100. And then you say, please enter the value of pi. It's not a math quiz. You don't want to make them type in the value of pi. You want to program it into your program. And so it's a constant. Now, there are some things called unnamed constants, right? This has a name. An unnamed constant is just when you use that value right there. You don't give it a name. You just type it in there. It's also called a literal. It's literally 3.15, you know, whatever. It doesn't have a name. Unnamed constants, also known as magic numbers or hard-coded numbers, should be avoided unless it's just something like to the power of 2, right? If it's part of a mathematical equation, great. You don't have to make it, you know, a constant or a named constant. But if you're doing something like some volume law in physics or something in chemistry where you have Planck's constant or, you know, some volume constant or whatever, you're not going to want to type in 22.4 there, because what if you then find out that they wanted it to be more precise and you were really supposed to type in 24.0038, and you don't want to have to go and fix that equation there. Find it in your code. It may be buried 2,000 things deep. Instead, you'd want to put it as a constant up at the top. Here's what they have to say about constants. It contains numbers only. It's a number that's not supposed to change. A string constant is something that's known as an alphanumeric value. I don't think I'm ever going to call it that. It could contain both alphabet characters and numbers, enclosed in quotes. Variables are things that can change, right? You can ask the user for the radius, and then you can convert the radius to a number. Or you could ask them for the radius a second time. The declaration is a statement that provides the data type and the identifier, and optionally an initial value. In this language, you don't give it a data type. The data type is determined by its initial value. So when you say total is equal to 0, we didn't have to say integer total is equal to 0. Now later on, you'll do some languages where you have to do that. So here's what I was talking about. That stuff that we did where we said total is equal to 0 and scores is equal to 0. This book would show us putting it in a box like that. Not that you have to make it a different color. That says declarations. And then you list your variables up at the top. If they have any starting values, you would also specify the starting values up here. And that's not a bad idea. I'm going to adapt that into my flowcharts that I do for the rest of the semester. Then you could do the rest of it. So if tax rate was going to be up here as well, or pi, then you can define that. Now the language actually does give you a version of pi in the math library, so you don't have to type in that pi is equal to 3.14159. You can use their version of it, which is obviously going to be much more precise. We probably have to 15 digits or 30 or something. So a numeric variable holds digits, and there's two kinds, ints and floats. You can perform math operations on it. A string variable can hold text, like the letters of the alphabet, or punctuation, numbers. Type safety prevents assigning values of an incorrect data type. Our language does not have type safety. It's a great idea. You know, if something is supposed to be a floating point number, then you better not have a string assigned to it. It's nice if the language refuses to let you put a string into it. So in those languages, such as Java and C and C++ and things like that, if you do this, int x is equal to 3, and then later on in your program you try to set it equal to like a floating point number or a string, it would flag that as a syntax error. It wouldn't even run. It wouldn't even compile. And you could fix it before you ran it. So type safety is a nice thing. This language doesn't have it. Scripting languages tend not to have type safety because they're not pre-compiled in the same way that Java and C are. So the identifier is a variable's name. There are rules for it. You're supposed to choose good and reasonable and descriptive names for values. In my code here, in my idle code, did I have to use score? No, I could have said x1 and x2, right? And then while x1 is not equal to, right? This is dumb, and I'm going to undo all these changes. X1 is equal to input, X1 is equal to score. You know, I should have just done a search and replace. And then if score is, you know, then X2 is equal to X2 plus X1. And then down here, print out X2, but not in caps. I said not in caps. Anyways, it works. It's the same thing to the computer. The computer doesn't care what we name this. We could have called this one Fred and Barney, or, you know, Tony and Stark, or whatever, you know. The names don't matter to the computer. They matter to the programmer. But when you're writing code, you're not only telling the computer what to do, you're telling the next person to look at the code what it's doing. And typically, you write code only once, but it gets read a lot, right? You know, if you ever need to fix it, you have to go and read the code. If you're part of a large programming team, it's going to go through a review process where somebody else comes and looks at it to make sure that it looks good. At some programming departments, they actually pay to have two programmers looking at the same screen. You have a buddy system. One person's typing, one person's watching, and then maybe you swap off occasionally. That would drive me up the wall to have to code with somebody watching. You know, so I would prefer not to work at a place like that. I never had to. But some places do. Maybe if NASA had two programmers per screen when they were creating that, you know, that space probe, you know, code, maybe they would have caught it before they wasted their $1.5 billion. All right, I'm going to undo all that. You choose good variable names. One-letter variable names are not good variable names. Now, when I'm typing examples, I will tend to use one-letter variable names or short ones because it's easier to type, right? People type in, give typos, right? You know, as I'm wandering around, half the problems are typos because, you know, people spelled, you know, input wrong or swapped two letters or whatever. And when I'm typing in my little notes on Notepad, I may also give one-letter variable names. But as far as a real program goes, you should give good names, descriptive names. There are some rules. This will be the last thing we talk about for variable names, also known as identifiers. Here are the rules in this language because sometimes they differ. Variable names, also known as identifiers, have to follow rules. You can't just call, you know, a variable anything. When I said it doesn't matter to the computer, it still has to be a legal variable name. The rules are, has to be letters, digits, or underscores. That's it. So no spaces. Spaces are not listed as one of the optional things. So tax rate is perfectly good. Tax rate 1979 is a good variable name. Tax space rate, bad variable name. It's got a space in it. Tax rate $, well, according to these rules, that's a bad variable name because it only allows underscores. Now, some languages do allow $signs. Honestly, I can't remember if Python does or not. Well, you can find out real fast. Not WordPad. X $sign is equal to 3? No. Okay. So, yeah. Also, the next rule. Where'd my rest of my line that said underscores? Has to be letters, digits, or underscores. Cannot start with a digit. So tax rate 1979 is great, but not 1979 tax rate. You can mix uppercase and lowercase to make your values easier to read. So instead of patient height, you could use patient height, like that. You could also use underscores. Now, I learned programming in an era where people did it that way. Nowadays, this is the common way of doing it, using a mixed case to read it. So you may see code done either way. In some languages, this is so the norm that I don't even ever do it the other way. Maybe Python's the same way, I don't know. So, but I don't care how you do it in this class, as long as you're picking variable names that mean something. Not pH for patient height, right? Because what is pH? Sounds like something to do with acid, and base or whatever. Doesn't sound like it means patient height. Or patient temperature, PT. That'd be a bad variable name. Alrighty. So these are our rules for variable names. Letters, digits, or underscores cannot start with a digit. No spaces is actually part of the prior rule. And lastly, should be meaningful. Now, does that mean that they can never be? Well, no. Counters, numbers that just go up by 1 for a loop. Those are about the only time single letter variable names are allowed. Like for I this is not valid Python, but in some languages it is. For I is equal to 1 to 100, like that. Print I. If that's all it is, then why expand the word I out to the word counter, right? Single letter variable names are okay for counting loops, but otherwise you should give good variable names. So these two are hard and fast rules, and this is just a recommendation, guideline. I guess I'll throw in TR as bad just because it's too short. Not descriptive. All right, guys. I think we're done for today. I didn't make a homework assignment. We're kind of not doing enough homework assignments, but since I've been giving the quizzes and stuff like that, we'll do another homework assignment on Thursday.